thanks everyone for joining. Today, the topic is to discuss the new HydroForecast short-term model that we built. We're calling it ST-3, third version of our model, and give a little bit of background on the motivation for building it, what it is, and the impact that we expect it to have for our customers and users. So just one intro slide on upstream tech, if you're unfamiliar. We're about 40 folks working across two products. One of them is called Lens. It's a remote sensing platform where folks can monitor lands and land use change from their desk. And then HydroForecast, which is what we'll talk about today, our product that forecasts stream flow across 14 countries and 5 continents. So just a little bit of context and background. Inflow is really inflow in a stream, a river, coming into a reservoir is a really important part of managing water. It's sort of the top of the pipeline for many, many decisions that come afterwards. And some of the use cases and reasons why inflow is so important are for energy, safety, compliance, and operations. So there's lots of different use cases, but the two that we're going to focus on today that are particularly important for a short-term forecast are safety and operations, and then also for energy production. So a couple examples here. Use case number one. When you have an event coming in, operators, there's some of you on the call now, some of our customers, it can be very stressful. There are certain times of year, for example, the snow melt season, when you actually know that you're going to get this snow melt peak, but you don't know what day of the week it's going to be. And the magnitude, the timing, all of that is uncertain. And it's a very complex problem to resolve. And so one of our goals with HydroForecast is to help make that easier by having a more accurate forecast days ahead. Now, the snowmelt season, like I'm showing here in this little animation over the spring, that's kind of a known forecast. You know something's going to come in. We also have unexpected events, and those events are even more difficult. You might have rain on snow, where your reservoir is already kind of full. You might have convective rain that dumps a huge amount of water. And so those are really important for managing safe operations and ensuring that you don't have downstream consequences. So really important to have a good inflow forecast there. The second use case, and many of our customers use our forecasts, our short-term forecast, for understanding how much power they can produce from hydropower assets. So this graphic is showing the growth of renewable power since 2014, from about 22% to about 30%. And hydropower here still has the majority share of that renewable resource. And hydropower plays a critical role in helping us make a reliable renewable transition. And so every drop of water you can think of as a dollar or a megawatt or a piece of a megawatt. And so having a forecast and being able to schedule and optimize for power is super important. And so with that, even though we have a great forecast already, our current forecast is the best you can get on the market, any additional gains are significant. And that means being able to forecast a little bit better the timing and magnitude of an unexpected rain or snow melt. Same thing with energy. And so our team is motivated to help with that challenge. That's what drives us as scientists and engineers. And so really where we started, why we building ST3, at the heart of it is improving accuracy. And so we asked ourselves, all right, if accuracy is what's most important, where can we get a step change? We've already squeezed a lot out of our machine learning model. And we were able to show good accuracy over a 10-day period, but we want more and our customers want more. And so where is it that we can find more accuracy? And if I was in a room with all of you, I'd sort of ask for hands and you know, get your thoughts on this. But I think you won't be surprised that where we think we can get the best accuracy is by including more weather forecast data. So better data, more frequently, from more sources. Great. Well, if only it was that easy to just go grab a bunch of weather sources. Not so fast, as we say in science and engineering. There's always, usually something we've got to solve first. So the good news is that there are a couple of challenges that were ways that we needed to fix in order to get to the ability to ingest lots of different weather types. And I say the good news about that is that these two challenges that we sort of innovated on are pretty novel for science and especially for neural network hydrology. So we're going to be talking about those in blogs and publishing on them, talking about them at conferences. But I'll kind of go through them in a little bit of detail. So bear with me a minute. Okay. On the left is a appropriately complicated diagram of weather forecasts, issue, and time horizon. So right now, our HydroForecast ST-2, I'll call it, uses these top 3 weather forecasts. So that's the pink one, that's NOAA's GEFS, then ECMWF, HRES, NOAA GFS. And those forecasts come out for different horizons. They're issued at different times of day. And right now, we've actually simplified it. We take the 0Z and 12Z forecasts, and that's when we update our models with new weather. But we know that having more frequent weather is important, and there are some forecasts that don't issue for a 10-day period every 12Z. For example, HRRR. So NOAA's HRRR is a North American, US-focused, high-resolution data set, precipitation and temp forecast that comes out every hour. It comes out every hour, but only every 3 hours, and then every 6 hours, it changes its horizon. So it's a kind of a complicated source to integrate into our forecast. And then we have a bunch of machine learning weather forecasts that are emerging. They're coming out. Folks are starting to use them. And we're not even sure what those horizons are. So for any hydrologic model, that's physical model or neural network model, you actually need a value for every single input time step. So if it's precipitation, if it's temperature, you can't have a bunch of NAs. NAs will cause the model to crash. Now, hydrologic models just don't handle this very well. But we know we need to fix this because what we do right now, and it works pretty well because we have values for every time step, is we and others in operational hydrology, they will interpolate, they'll use a filler value. We'll say, okay, well, let's just use yesterday's value or the hour before, or let's use the last 3 days and take an average. And that can work okay, but we know that value is not correct. And if we're going to integrate HRRR, which only goes out 48 hours, and we're making a 10-day model, that leaves about 8 days of filler values. And we know that wouldn't work very well. So we had to get around this challenge. We had to build a way for the model to not just use a filler value, but actually learn that that data is not there. And I'll talk about how we did that next. So that's one challenge. We're dealing with lots of different complicated weather forecasts, and we need a way for the model to be able to learn consistently how to use the weather. The second challenge are these very same weather inputs are subject to delays and outages. If you don't have a weather forecast, it's pretty darn difficult to get a hydrologic forecast. These are some of the outages and delays that we've cataloged the last year. Currently, our model actually handles this because an on-call engineer will go in and make a code change, especially if we have some notification about the outage or the delay. We can go do that before the customer experiences any delays. So there's still a buffer. We're able to deal with that on our end pretty well, but there must be a better way. So this was the second challenge. And so our overall goal with ST-3 is to have a new model with improved accuracy and flexibility so we can integrate new weather, then increase how often we're getting that weather. So be able to get the latest weather and use that in the model as often as we can, because we know that during peak events, that's really important. And then our third goal is to add more interpretability, add more information about what those forecasts are saying and give that to our users. So that's kind of the next up, and I'll talk about that at the very end. All right, so how did we do what we did and what did we build? So the first thing that we focused on was building a new model, a new short-term model. And the first challenge we needed to deal with is that thing I was talking about where the weather inputs are at different horizons, they go for different lengths. And so what we did was actually something quite novel in neural network hydrology, which is to say, okay, if this ST3 box is how the model is used to seeing data, so I'll just walk through it. If there is a value, use it. If there's not a value, use the last X number of values, give me an interpolation, and I'll use it. So this is all pre-processing in the weather part. The hydrologic model hasn't yet seen this. With ST3, we did something a little different. We said, okay, if the value's there, great, use it. If the value's not there, I'm going to replace it with a crazy number, crazy negative number that the model would never see and try and use to make a prediction in the hydro forecast. So what we did was we introduced all of this missing data into the model randomly. And we did that with her, which was already missing 8 days. And then we took data randomly out of our GFS feed or our GEFS feed or our ECMWF feed. And we made this sample data set that contained randomly missing values. And we had the model train on that. And so what actually happened was the model dynamically learned that it shouldn't try and fill that value. It should use a different data source. And because our model has multiple weather forecasts, it doesn't try and use that data stream. It goes and grabs what's available. And what ended up happening was we validated that the model does just as well with this system, with all this missing data, than it does without it. And that was pretty exciting. And that's something that we'll be definitely kind of talking more about in a technical way in some papers. Okay, great. So we have this way to deal with missing data. Now we can integrate her and any other data source that has different time horizons. Okay, the second thing that we did in this new model was we built a new architecture. And bear with me here, I've got some upstream tech pets that I'm going to use as a metaphor to explain what we call data augmentation. Okay, data augmentation. The example I'll use is something called computer vision, where you have an AI model that's trying to learn the image of a cat and the image of a dog. So we wouldn't want to confuse cats and dogs. We want this model to learn what a cat looks like and what a dog looks like. And to do that, we have all these pictures of cats and dogs. And so we have this training data set full of samples. Now, we don't have that many samples. And so to make more samples, to train the model better, we might take the picture of the cat and turn it a little bit. We might zoom in on its ear. We might zoom out. We might turn it this way. And that's called augmenting the image. And so by doing that over and over, you create a bigger sample set. Okay, and so now you have many, many more samples to train your computer vision model, and it's going to learn a cat and it's going to learn a dog. Now, bring that over to how in the world does that relate to HydroForecast 3? Okay, bring that over into our world of hydrology. We have a core model that's trained on about 500 basins, 489 to be exact. And in that training set, we've got 5 years of data, 489 basins, hourly data, and we create this sample set. And right now, the model is trained on about 1 million samples, which is pretty good. But what we can do now that we've built this adaptation that I talked about in step 1 is we can actually augment that data set, and we can add noise to it and add this -999 crazy value here, add it over here, and essentially augment the input data set. So this is all happening kind of in the weather and inputs. And so when we go and train the model, there's actually an infinite number of samples that we can pick from. Currently, ST3 is training on about 600 million samples. So we've increased that number of training data set, I don't know, 60-fold. Which means we're going to get a better core model. And that core model is what we use when we go to a new basin and tune to local information. We always start with that core model. So that's another new thing that hasn't really been done in neural network hydrology. And so we put these two things together. And the question is, what happened? What did we see? So this is a plot that's showing across all 489 basins that we train on. So it's not a tuned model, it's just a core model. The difference in RMSE, which is an error metric, where you want to be at 0, that would be great, and across lead times. And so this is over our validation period, which is about 3 years long. Essentially, we reduced our RMSE by about 12% compared with the model in production. So the model in production is that black line. Pretty good. We see, like we expect, a degradation as you go to longer lead times. Then the green line is the ST-3 model without her. So the difference between the black and green line is really that data augmentation. We're training on many, many, many more samples, but we hadn't put in her yet. Then the orange line is including her. So we've really dropped the RMSE down quite a bit, especially in the first 2 days. And that's because the horizon of her is 48 hours long. So we're pretty excited to see that. So that's where we begin. We begin with this core model. Now I'll show an example from a customer site to give you a sense of the impact or what customers are experiencing with the new model. So on the left, I'm showing a spring rain event. On the left-hand side, and sorry, that image is a little dark, we've got ST2. So that's the model before. We put in ST3, which is on the right. And you can kind of see it's a little subtle, but it can be important, especially on the day ahead, where the model on the left didn't quite capture that dip below the peak. And then the timing of the peak was a little bit late. And then it was high bias on the tail. On ST3, really narrowed down those peaks and the troughs there, and then brought the bias down. Those are really long lead times, 8-9 days ahead in that model. So pretty excited to see that. Great. Okay, so we have this new model. We've added her. What's next? Well, with all the things I just showed you, that's only pulling in weather every 0Z and 12Z. So the next step is to add more frequent weather. We know that a better forecast more frequently, especially from a high resolution data set like her, is going to give more accuracy over a peak event. So right now, our model sees all these different sources at 0Z, ECMWF, GFS, GEFS, and her. Let's go 3 hours later. We don't have a new ECMWF, GFS, or GEFS forecast. All we have is a new her forecast. Okay, we want to be able to pull that in. Then we go 3 hours later. Now we have a new GFS forecast and a new her forecast. So we want to use that in the model. And so we've built this way to stitch together different new forecasts so that the model can always pick up on what's the latest. And this is kind of a schematic that tries to show that. In other words, we start at 0Z, we get something new at 6Z, we get something new at 9Z, and at the bottom there, we kind of blend it all together. And this is all done seamlessly in our kind of input processing, all within the weather data. And so we're stitching together this kind of patchwork of the latest weather across the different sources available, giving the model the best chance it has to make a good forecast at that hour. So what's the impact of this? I'll show one example here from a site this is in June. ST3 there in the blue is everything up without that latest weather patchworking together. The orange line is when we are able to get the latest precip and temp forecast from each of those sources. We end up higher on the peak, better on that peak flow over this event. This is a pretty big event going from basically 0 to 25,000 CFS. So pretty decent forecast. So now in areas that we are getting her, we're getting hourly, 2-hourly updates of her. If we don't have her available, so outside the continental and some parts of Canada, US, the weather will update every 6 hours. So very cool. So those are the two things that are out there now for folks that we've migrated over to ST3. The thing that's next is something that's going to be showing up on the dashboard in the next couple weeks. And that's what we're calling our single source traces. So I'll kind of walk through this. So now that we've built this way for the model to make a prediction without different sources, what that's opened up to us is the ability to do single source traces. And some of our customers are used to seeing like, well, what if you only had a GFS driving your forecast? What if you only had a GEFS? And so now we can actually show that on our dashboard because we're making those under the hood with ST3. Now in all of our training, all of our validation, the blended forecast, so that's the blue line there, that is our best forecast. That is using all available weather at the latest times. And we've shown in publication, and we continue to show in operations, that that's going to be the forecast to use for decisions. This single source is sort of an experimental forecast. We're really interested in how customers would use it. We want to get a lot of feedback on that. but we've heard that it would be interesting for folks to see. So we're kind of putting the final touches on how we're going to show that on the dashboard, and we'll be in touch with folks for that. So I'll just kind of walk through this example. Here we are at a rain on snow event in the Pacific Northwest. Rain on snow, particularly difficult for weather models and hydro models because you've got the temperatures fluctuating around 0. So that's over here, if you can see my cursor. And a couple things to note. So this orange forecast is GFS only. That forecast is high at the longer lead times. And that's because the temperature forecast never went below 0. It was always above 0. And that made the difference in being able to say, is this going to freeze or is it going to run off? The blue forecast, our blended forecast, had all the precip forecasts in there, was able to make good sense of the information it had, and it got the peaks pretty darn well, as well as a recession. So that's an example of something that we are going to be putting out and getting some feedback on. And I'll just show one more example here. So this is from a rain event in the Northwest. And one of the reasons for showing this example is just the value of HRRR having a more frequent high resolution data source. So the HRRR precipitation is the largest, the highest line here in the bottom plot. And that's really helping our blended model, the blue line here, capture the peak because the other sources weren't quite as high. They didn't quite predict as much precip. And so that's really what helped drive that forecast up there at the top. So we're pretty excited about this and curious how folks are going to use it. But being able to see these kind of things and say, well, what if this happened? What if that happened? Is helpful, I think, for all of us to be able to help interpret what's happening with the model. So on our roadmap, I'll just finish here with this slide and sort of a take-home slide. Essentially, we're excited about a few things that are in flight. So releasing these experimental single source forecasts is next. And following that, we sort of launch ST-3. As we do practically every August, September, we revisit our seasonal model. It's kind of the dead time for hydrology in most of the country and some parts of the world. And so we're going to be taking a lot of the ST-3 architecture that we built with the weather processing and the data augmentation and building that into our new seasonal model. Excited about that. And then the last thing is continuing to experiment with some of the new machine learning weather forecasts. So there's the AIFS that ECMWF has picked up. That's an entirely made AI weather forecast, and they're running that. Google is continuing to build on GraphCast and make certain experimental data sets available. And so we're poised now with ST3, we can kind of experiment with that quite quickly and understand its value add to the model. Cool. So with that, I will sort of close with a takeaway slide and open it up for any questions that folks have.
Oh, we have one question from Hayden Smith. Can you train the model with high fidelity model data? Oh, can you train 2 high fidelity model data?
Yeah, Hayden, what kind of data are you thinking of? I'm going to put you on the spot.
I was just wondering, you augmented the data, showed how you increase your sample size, dramatically. Is there a way, so you say you had 500 basins that you're training to, do any of those basins have like high fidelity HMS or RAS 2D models that you could either wait or trust enough to, say you ran some stochastic storm transposition and got some really big unseen events like a Hurricane Harvey that none of the other 500 sites have ever seen, and bring that into the training set?
Yeah, that's a good question. We haven't included, data that is outside of, we have weather data, we have satellite data, we have land characteristics, we have stream flow observations. We haven't yet trained the model on RAS data or something like that, but I think it's possible because we have a semi-distributed model where we break the basin up into small basins. And so if we have kind of reach scale or a little bit coarser than that, I think we could actually use the data to help with that. It's a good thought.
Thanks.
Thanks, Dean. I see one other question about how far can we, how far can the model forecast? I think that's the question. And so our short-term model goes out 10 days, and that is the window that we forecast across for the short term. And then we also have a seasonal model that can go a year ahead, which integrates sort of the short term along with like seasonal patterns, and then blends back in with climatology at the end.
We got two more. We have one, same person. What has been the accuracy of our long-term forecasts?
Yeah, long term, I think everybody has a different long term. If you're talking about the year forecasts, it depends on where in the world. In rain-driven basins, it's pretty difficult. We were just doing a validation for a rain-driven basin where we had skill over the long-term average out 60 to 80 days, which is pretty darn good. In a snowy basin, we see skill out to longer horizons in particular areas, but sort of depends on the dynamics there. I see one other question. Have we gone back to check our forecasts with what actually occurred in the basin? Yeah, it's a good question. So every time we train, validate, put out a new model, we go and validate the model. So we have a period where the model doesn't get to see observations and we just compare them. And that happens every time we set up a model. I'll just go back here. This validation here is all validation period. This is not, the model didn't actually see what was happening during this period. So this is the error on what actually happened versus our forecasts at different lead times. And then, like, for example, here, this is just sort of a live validation where you can see how well the model was able to pick up on, but we calculate a bunch of statistics every time we set up a model.
Thanks. There's one more question there. Given the different and dynamic bias of each weather forecast, can the weather forecast picker decide to not choose a particular updated forecast during blending if it is historically not performing well?
That is a great question. So we don't explicitly give the model any biases or weights on different forecasts, but during the training period, that is sort of what it's learning inherently and implicitly. It learns which one to rely on more. And some folks have actually asked us if we can go, take a look at how the forecast paid attention to each one, because we have that tool internally that looks at, okay, how much did the forecast pay attention to each input, and actually like calculate a histogram showing which inputs it was paying most attention to. We don't do that currently in like a real-time way, but we do that internally. So it is doing that. It's just we aren't actually then implementing something that says, okay, now that you know that, don't use that weather source. We just allow it to do that kind of dynamic picking in real time.
Nice. Well, I think those are all the questions we have. We will be sending this recording out after the call, but thank you all for joining. Laura, is there anything else you have to say?
No, thanks everyone. And feel free to contact us with any questions or further thoughts.
Cool. Thank you all. Have a great Wednesday.
Thank you.